All right, we're starting chapter 11 today on vector valued functions, and we're getting dangerously close to this actually looking like a calculus class. Just one more section here. All right, so a vector valued function, what is it? In R2, R3, I've got the definitions there. These are functions that take a real number as an input and output a vector, either in 2D or 3D. Okay, so you have these component functions, we call them. And they are the functions that define the x component and the y component, or the x, y, and z component of a vector. So let's take a look at an example of a vector valued function. All right, so here we have r of t defined as t squared, comma 1 over t minus 1, comma root t. Three different functions for the three components of the vector. And we're just asked to evaluate r of 4. That just means what you would think it would mean. We're just going to plug in t equals 4. Okay, so 4 squared, comma 1 over 4 minus 1, root 4. And this is all it is. We plug in one number, 4, and then it spits out a vector, which in our case is going to be 16. 1 over 3, root of 4 is 2. And that's it. Okay, each real number gets associated with a vector. The next thing they ask us to do with this function is to state the domain of the function. It's probably been a minute since you thought about domain. Let's kind of remember our domain rules from algebra. So remember, we're living in the world of real values. So for example, we don't want to take the square root or really any even root of a negative number. We say that's not allowed. Okay, that includes like fourth roots and sixth roots. Let's see, what else can't we do? We can't divide by 0, so no stuff over 0. And let's see, there's lots of other rules. Logarithms, you can't have a negative number in a logarithm or 0. Tangent, secant, cosecant, they all have domain rules, things you can't plug in. But for now, this is going to be sufficient. These are algebraic function rules. Stating the domain of r of t. So we want to make sure that we don't take a square root of a negative number and that we don't divide by 0. So let's think about our number line for our values of t that we could plug in. So automatically in the middle there, I see that I can't plug in t equals 1. That would cause division by 0. All right, so on my t number line, I want to come over here to 1, and I want to cut out that value. Okay, so I would do that by putting an open circle there. So we want to include things that are not equal to 1. And then, let's see, our first function actually was t squared. I kind of skipped that one. You can square any value of t that you'd like. So that one doesn't give us a domain restriction. And then root t, I need to make sure that I never put a negative number under that radical, right? So we want to cut out all of the stuff on the left half of the number line. We only want to keep on the right half. So I'm going to come and shade the right half after 0 where it's positive, skipping over 1, right? We don't want to include 1 because that offends the y component function. Okay, and let's think about that boundary value 0. We can take the square root of 0, right? So I want to include 0 in my domain. That's okay. All right, so we want everything greater than or equal to 0, excluding 1. So you can put this in either interval notation or set notation. Set notation is probably easier. This is the one where we would say all values, I'm in algebra, all values of t. How about that? So that t is greater than or equal to 0, comma, t is not equal to 1. Okay, so that just lists all of our restrictions for that area of the number line. Interval notation is perfectly acceptable. We'll say that t goes from 0 to 1, but not including 1. Remember, the square bracket means include it. It's the same as that filled in dot. And the parentheses on 1, let's see, means don't include 1. And then we say also, that's the U for union, 1 to infinity. All right, so either one of those are acceptable answers for domain. All right, so those are not too hard. Next video, we're going to talk about graphing vector valued functions.